We are going to discuss today the colligative properties. Now, colligative properties. These are the properties of the solution. When non-volatile solute is added in the volatile solvent. Non-volatile means it is having very low vapor pressure, while volatile means least moderate vapor pressure. The colligative properties for a given solvent, it depends only on the concentration of the solute and not on the nature of the solute. This characteristic can be exploited to learn something about the solute. Most commonly, it is used to determine the molecular mass of the solute. The colligative properties that we will discuss include the vapor pressure lowering, boiling point elevation, freezing point depression, and osmotic pressure. In dilute solution, these properties depend only on the number of solute particles present and not on their identity. So they are called as colligative, means depends on the collection, total collection, not on what is collected. Quantity, it depends on the quantity. So it is known as colligative property. Now we assume that throughout the process that the solute is not volatile, so it does not contribute to the vapor. We also assume that the solute does not dissolve in the solvent, that is pure solid solvent separates when the solution is frozen. This assumption is quite drastic because it's true for many mixtures. It can be avoided at the expense of more algebra, and that's why there is no new principle. Now we will see vapor pressure lowering. Now dissolving a non-volatile substance in a solvent which is volatile, it results in the lowering of liquid's vapor pressure. This phenomena is considered by adding the effect when the non-volatile solute is actually added, and we can see the vaporization condensation process. Now, the rate of condensation, it is unaffected by the presence of the solute. The net result is vaporization condensation equilibrium is achieved with pure solvent molecules in vapor phase, that is at a lower vapor pressure. While this kinetic interpretation is useful, it does not account for several important aspects of colligative nature of vapor pressure lowering. The property entropy that we will discuss. Now, for the purpose of understanding the lowering of liquid vapor pressure, it is adequate to note that greater the entropy of solution in comparison to its separate solvent and the solute serves to effectively stabilize the solvent molecule, and it hinders their vaporization. A lower vapor pressure results a correspondingly higher boiling point as described in the module. Consider the solution of a non-volatile solute in a volatile solvent. The vapor pressure of volatile solvent will be decreased due to the introduction of the solute. The magnitude of this decrease can be quantified by examining the effect of solute. In order to establish the equilibrium, the chemical potential of the two phases must be equal. Means chemical potential of vapor will be equal to chemical potential of the liquid phase solvent. You have studied this property in 12th also, but with chemical potential we will reach to Raoult's law, and after that you know how to reach to the molecular weight. But from this equilibrium of chemical potential we will first reach to the Raoult's law. If the solute is not volatile, the vapor will be pure. So we can assume the ideal behavior, and we can use the equation here, where this P dash is nothing but the vapor pressure of the solvent over the solution. Similarly, for the solvent in equilibrium with its vapor, we can write down this equation because only vapors of the solvents are present. So it will behave as good as a pair. So we can write down mu 0A for the solvent. Now we know the value of mu 0A. So by combining these equations we get this. Now RT can be cancelled and we reach to such expressions, which finally reduces to this. This is the Raoult's law. So we reach to the Raoult's law. Now, after this Raoult's law, we can easily replace this for another composition, another mole fraction, and from the mole fraction we can keep the values of the pressure. We can find out the value of x2. This is the value of x2. The left hand side, it is mentioned earlier, is called as relative lowering of the vapor pressure. Relative lowering of the vapor pressure. And it can be used to find out the molecular weight, where mole fraction we can convert into number of moles, and which can be number of moles can be successfully converted into the molecular weight and the weight taken. W and W2 are the weight or masses which has been taken for solute and solvent, and M1 and M2 are the molar masses of solvent and solute. From this equation, we can calculate the molar mass of the solute. This you have studied in the previous class, from this onwards. But the different thing is, you have to consider the chemical potential, you have to reach up to the Raoult's law, and after that, this expression you have already studied in your 12th standard. Various numericals can be asked on this equation. It has been asked to calculate the weight of solute or solvent or the molecular weight. So you have these equations. So we are going to study 4 such equations for 4 colligative properties for calculating the molar masses. Now, second is the elevation of the boiling point. Now, in elevation of the boiling point, we can see in the figure variation of vapor pressure with pure solvent. And the solution, it is a function of temperature. So similar to lowering of vapor pressure, the elevation of boiling point also depends on the number of solute molecules rather than their nature. Means again quantity, not the quality. Means as we have discussed in the last unit also, that the solution of 1 mole of sucrose and the solution of 1 mole of urea, they will boil and show the same effect. The heterogeneous equilibrium which exists. So we will denote again solvent by A and solute by B. The equilibrium which is established at a temperature for which we can write down this one. The pressure of 1 atmosphere, it is same throughout and it will not be changes. We show in the justification that the equation implies that the presence of solute at a mole fraction Xb causes an increase in normal boiling point from T star to T plus delta T. We can take it. So from this we can calculate ln XA, where delta vapor G, this is the Gibbs free energy of vaporization of pure solvent. Now, using Gibbs-Helmholtz equation, we can find out its value, which can be kept here. Now, following some mathematical steps, multiplying both sides by dt, integrating it within the limits 0 to this and then T star to T, we will get such type of expression. Now it reduces to delta T, Kb is M, where M, it is the molality. M is the molality. Number of moles of the solute dissolved in 1 kilogram of solvent C, it is focused on the number of moles only. And this constant of proportionality Kb, it is known as boiling point elevation constant or molar elevation constant. Ebullioscopic constant, its unit is this. Again we can convert that M in W1, W2, M2 like this, and from that equation which we can find out M2, molar mass of the solute, if all these parameters are known. So this is about the expression for depression in the boiling point. We have seen the vapor pressure and boiling point in this talk. Again, the numerical can be asked in the exam on these two equations, also on another two, also on all the four colligative properties. The other two we will discuss in the next talk. So you have to prepare these two equations. You should derive it at your own and practice the numericals on it.